today's Vidyanagar online science class. We are going to start a new lesson, magnetic effects of electric current. And at the end of today's class, you are going to learn magnetic field lines and their properties. Let's begin our today's class. The very famous physicist Hans Christian Ørsted proved that electricity and magnetism linked each other. Electricity and magnetism linked each other, which means with the help of electricity, we can make magnetic property on some materials. Such magnets are known as electromagnets. The magnets made by using electricity. Such magnets are known as electromagnets. So what is the magnetic property of electric current? The electric current carrying wire behaves like a magnet, or when we pass electricity through a metallic wire, this metallic wire behaves like a magnet. An electric current carrying wire behaves like a magnet. So when we pass electricity through a metallic wire, it behaves like a magnet. This is the magnetic effects of electric current, and such magnets are known as electromagnets, and these electromagnets are temporary magnets because they have their magnetic property only in the presence of electricity. When we disconnect the electricity, they will lose their magnetic property, which means electromagnets are temporary magnets, and electromagnets can be produced with the help of an electricity. That is magnetic effects of electric current. An electric current carrying metallic wire behaves like a magnet. So that is the magnetic property of electric current, and this concept was put forward by very famous physicist Hans Christian Ørsted. According to him, electricity and magnetism linked each other. We can make an electromagnet by passing electricity through a metallic wire. Okay, and see the magnet. Have you heard about the magnetic force? Yes, so magnetic force is a force exerted by the magnets, right? So these magnets exert force or influence that force in the region around it. So these magnets, when we place a magnet somewhere, these magnets exert its force or influence this force in the area nearby it, which means we can see their influence, or we can see we can feel the presence of the magnet in the nearby areas. That area is known as magnetic field. So what is magnetic field? Magnetic field is the area or space where the magnet exert or influence its force surrounding it, or it is the magnet exert or influence the force in the region surrounding it. So that is magnetic field. So the magnetic field is the area or the space where the magnet exert or influence its force. That area is known as magnetic field. So the magnetic field is the area or the region where magnet exert or influence its force. Okay, and when we sprinkle some iron powder over the magnet, you can see that these iron powder arrange themselves. Look at the picture. There you can see there are lot of iron sprinklings arranged themselves in around the magnet. So when we sprinkle iron powder or iron sprinkles over the bar magnet or over any magnet, you can see that these iron powder or iron sprinkles arrange themselves. Why they arrange themselves? Without doing anything, how these iron fillings are arranged themselves? Because a magnet exert its force surrounding it. A magnet exert its force or influence the force in the region surrounding it. That's why, because of this force, these iron fillings arrange themselves, and these iron fillings arranged in the form of lines. You can see that. Okay, so how this how the iron fill, how the means iron fillings arranged, these iron fillings arranged in the form of a lines. So these lines are known as, so we can represent the magnetic field lines in the form of a line. So we can represent the magnetic field in the form of lines, that is magnetic field line. So the iron fillings arranged themselves, and these iron fillings are arranged in the form of a lines, and these lines are known as magnetic field lines. So what is magnetic field? Magnetic field is the area or the space where the magnet exerts its force, and when we sprinkle iron powder over it, these iron fillings arrange themselves due to the presence of the magnetic field, and these magnetic fields can be represented in the form of lines, and these are magnetic field lines. Okay. So we can represent the magnetic field or field lines in the form of a lines. So they are magnetic field lines. So the lines around the magnetic field, they are magnetic field lines. And the strength of the magnetic field. The strength of the magnetic field can be shown by, or the strength of the magnetic field is shown by the degree of closeness of magnetic field lines, which means the magnetic field may be stronger or weaker. This can be shown by the degree of closeness of the magnetic field lines, which indicates, which means if there is more field lines, or if there is crowded field lines, if there is number of field lines together, if you can see such field is strong field. If there is crowded magnetic field lines, if there is more number of magnetic field lines, which indicates the magnetic field is very strong. Just like you can see, there is two poles for the magnet, right? North pole and south pole. So mainly where you can see the crowded field lines, you can see the crowded field lines at the poles, correct now? Where you can see the crowded field lines, you can see the crowded field lines at the two poles, which means the magnetic field is strong at the poles. Where is the magnetic field is strong? The magnetic field is strong at the poles. Why? Because there you can see more field lines, or there you can see crowded field lines. So if there is more number of field lines, which indicates the magnetic field is strong, or its force is very high. So the magnetic field line, or it is strong, means it indicates there you can see, or there you can draw more field lines. And if the field lines are very close to each other, right? If the field lines are close to each other, that also indicates the strength of the magnetic field, which means at the poles you can see more field lines, but when we come towards the middle of the magnet, there you can see, there is a gap between the magnetic field lines. The gap between the magnetic field lines indicates what? The gap between the magnetic field indicates the field become weak. So if the magnetic fields are very near to each other, very close to each other, if we can draw, the magnetic field lines very near to each other, or if there is little gap between the magnetic field lines, which indicates crowded or many. So if the gap between the magnetic field lines are very less, which indicates the field strength is very high, or if there is gap between the magnetic field lines, which indicates the field strength is weak, or the field is weak. So on the base of that, you can see that at the poles, the field strength is very high, because more number of field lines or crowded field lines you can see at the poles. And when we move towards the middle, or when we far apart from the poles, when we reach at the middle, you can see the field lines, there is a gap between the field lines, which indicates the field become weak. So the strong field at the poles, and when it is far apart from each other, the field strength or the field become weak. So the magnetic field is strong at the poles because there you can see more number of field lines. If there is crowded field lines, if lot of field lines are there, or there is very less gap between the field lines, which indicates the field is strong, or if there is enough gap between the field, which tells you the field become weak. Now we can discuss about the properties of magnetic field lines. Which are the properties of magnetic field lines? So for that, first we have to draw a magnet. Okay, so a bar magnet, and then I need to mark the poles. This is south pole and north pole. So the first property of the magnetic field line, see, listen carefully. The magnetic field lines are emerges from the north pole and merges at the south, and inside the direction of magnetic field line is from south to north. So what is the first property? Magnetic field lines emerges from the north pole. Emerges from the north pole means it starts from the north pole, right? So the magnetic field lines are emerges from the north pole and merges at the south. Merges at the south means it goes through, okay? So it starts from the north and it goes through the south, and inside it is from south to north. So what is the direction of the magnetic field lines inside the magnet? It is south to north. So the magnetic field lines emerges from the north, merges at the south, inside it is from south to north. So magnetic field lines are emerges from the north pole, merges at the south, and inside it is south to north. So what is the first property of the magnetic field lines? Magnetic field lines emerges from the north and merges at the south, inside it is south to north. So it starts from the north pole and merges at the south pole. Okay, so it starts from the north pole and merges at the south, and inside it is from south to north. So the magnetic field lines are emerges from the north, merges at the south pole, and inside it is from south to north. So what is the direction of magnetic field inside the magnet? It is from south to north, and outside it starts from the north and merges at the south, and inside it is from south to north. So magnetic field lines are emerges from the north pole, merges at the south, and inside it is south to north. Starts from the north and goes through the south, and inside it is south to north. So the magnetic field lines are emerges from the north pole, merges at the south, and inside it is south to north. Okay, and the second property, the magnetic field lines are closed curves. The magnetic field lines are closed curves. Why the magnetic field lines are closed curves? Because why they are in the form of curves? Curves. So this is curve, no? Why they are in the form of closed curves? Because they emerges from the magnetic field lines, emerges from the north, merges at the south, and inside it is from south to north. So the magnetic field lines are closed curves. Why the magnetic field lines are closed curves? Because the magnetic field lines are emerges from the north pole, merges at the south, and inside it is south to north. That's why the magnetic field lines are closed curves. So two properties we discussed. First one, magnetic field lines emerges from the north pole, merges at the south, inside it is from south to north. Magnetic field lines are emerges from the north, merges at the south, and inside it is from south to north. And the second one, magnetic field lines are closed curves. Why the magnetic field lines are closed curves? Because the magnetic field lines are emerges from the north pole, merges at the south, inside it is south to north. That's why they are closed curves. Okay, and the second one we already discussed. The magnetic field lines are crowded at the poles. Magnetic field lines are crowded at the poles. Why the magnetic field lines are crowded at the poles? Because the magnetic field is strong at the poles. So the magnetic field lines are crowded at the poles where the magnetic field is strong, and nearby the middle the magnetic field is weak. So the third property, there are crowded magnetic field lines near the poles where the magnetic field is strong, and nearby the middle the magnetic field is weak. So at the poles strong magnetic field, and at the middle weak magnetic field. And the fourth one, magnetic field lines never intersect, never join. Magnetic field lines never intersect each other. Magnetic field lines never intersect each other means never cross or never join. Why? Because there is only one direction for the magnetic field. If magnetic field lines are never intersect, if they do so, if they intersect, which means there is two directions for the magnetic field, that is not possible. There is only one direction for the magnetic field, north to south, and inside it is south to north. So if the magnetic field, intersect, which indirectly tell us that there should be two directions for the magnetic field, that is not possible. That means the magnetic fields never intersect each other. The magnetic field is never intersect each other because there is only one direction. If they do so, there should be two directions for the magnetic field, that is not possible. And the last property of the magnetic field, if the magnetic field is parallel, or if the magnetic field is parallel, which indicates the magnetic field is uniform inside the magnet. If the magnetic field lines are parallel, if the magnetic field lines are parallel or equidistant, which indicates that there is a uniform magnetic field. Normally inside the magnet there is parallel lines which indicates there is a uniform magnetic field inside the magnet, and outside it is north to south and inside south to north, and inside the magnet the field lines are indicated as the parallel lines. So if the magnetic field lines are parallel, if the magnetic field lines are parallel or equidistant, which indicates there is a uniform magnetic field. So which are the properties? The magnetic field lines emerges from the north, merges at the south, inside it is south to north. Second one, magnetic field lines are closed curves because they emerges from the north pole, merges at the south, inside it is south to north. And the third one, there is a strong magnetic field near the poles, and when it comes to the middle part of the magnetic field is weaker. And magnetic field lines never intersect each other. If they do so, there should be two directions for the magnetic field, that is not possible. And the last one, if the magnetic field lines are parallel or equidistant, which indicates there is a presence of uniform magnetic field. So the magnetic field lines are emerges from the north pole, merges at the south, inside it is south to north. Okay. Now we are going to discuss about magnetic field due to a current carrying conductor. Magnetic field due to a current carrying conductor. Look at the pictures on the screen. See, just observe that pictures. What you can see there, is there any difference between these two figures? So you can see the changes in the battery and also in the direction, and changes in the direction of the magnetic field. In the first figure, how the battery is connected, first positive and negative, right? And in the second figure, we just reversed the direction. There also the flow of electricity from positive terminal to negative terminal, but we just reversed it. You just tilted and kept there, right? So here in the first figure, first positive then negative. There also positive to negative, but they arranged the changed the arrangement. Okay, so when in the first figure, just you look at the direction of the compass needle. How that direction of the compass needle? In the first figure, the north pole of the compass needle pointed towards east. So in the first figure, the north pole of the compass needle pointed towards the east. And in the second figure, the north pole of the compass needle pointed towards the west. Which means in the first figure, the compass needle pointed towards the east, and in the second figure, the compass needle pointed towards west, means there the direction changed. Why there is direction change? Because when we compare the first figure and second figure, there the direction of current is opposite. In the both figures, direction of current is opposite. So when there is change in the direction of current, there you can see the change in the direction of the deflection of the magnetic field. In the first figure, north pole of the compass needle pointed towards the east, and the second figure, the north pole of the magnetic compass needle pointed towards west. The east-west, opposite of east, west. So when we change the direction of current, there is change in the deflection of the magnetic field, reflection of the compass needle, which indicates the magnetic field produced by a current carrying conductor is reversed. Or when we change the direction of the current, there is the change in the direction of magnetic field, which means by making changes in the direction of current, we can make changes in the direction of magnetic field. So by making changes in the direction of current, we can make the direction of the magnetic field. Clear? So by making changes in the direction of current, we can make changes in the direction of magnetic field. So that is the conclusion of this activity. When we change the direction of current, there you can see the direction of the compass needle deflection. Change in the needle of compass needle deflection indicates there is change in the direction of magnetic field. So when we change or when we reverse the direction of direction of electric current, there you can see the change in the direction of magnetic field. So we can make changes in the direction of the magnetic field by making changes in the current. We can change the direction of magnetic field by making changes in the currents. Very important point. Okay, so how can we make changes in the magnetic field? So we can make changes in the magnetic field by making changes in the current. And the last point, magnetic field lines are vector quantities because they have both direction and magnitude. So the vector quantities are the quantities which have both direction and magnitude, and for the magnetic field lines, they have both the direction and magnitude, so they are vector quantities. So we can make changes in the direction of magnetic field by making changes in the direction of current. Okay, so that's all about today's class. We just started our chapter, we completed the introduction. Okay, I'll come with new ideas in the next class. Till then, it's bye. Thank you for watching. Have a great day.